Good everyone, my name is Graphics. Today we want to be looking at another aspect of thermodynamics, which is refrigeration cycle. And this refrigeration cycle will be looking at what is called coefficient of what? Performance. Now we know very well that the coefficient of performance, COP, is the ratio of the desired effect over what? The network or the work net. So now the COP that we discussed earlier, we said in a refrigeration cycle or in Clausius statements we have two consequences, which is the heat pump and the what? The refrigerator, and they are both reverse heat engine, right? So your refrigerator can work as a heat pump, and the refrigerator can be used in heating purpose, and can be used for what? Cooling purpose too. Now, if we are talking about the refrigeration effect of a refrigerator, talking about the COP of a refrigerator, that is, this C arrow means refrigeration cycle. Now, in your refrigerator, what do you expect? You expect cooling. Am I correct? So we have it to be the desired effect. What we desire from the refrigerator is cooling. Correct? So cooling over what? The work net, or I put it the work in. Now this cooling happens in the evaporator, because we say evaporation causes cooling, right? It happens in the evaporator, and the evaporator on its own happens in between state what? State 4 to 1. The evaporator happens in between state 4 to 1. Or before it goes to 4 to 1, cooling will now have Q. From here we have this will be equal to what? Q 4 to 1. That is where from state 4 to 1 there is cooling, right? Over what? The work in. Also, I can easily say that for my Q4 to 1 at the evaporator there is heat addition. So I can put Q HA all over what? The work in. Any of them I want to do. So there's always heat addition at the evaporator. How good? So you can take any of these three models and move forward. That is for what? The refrigerator. Now, in terms of temperature, my COP, let me put it this way, in terms of temperature, right? The COP at the refrigerator will give me. Now I said something earlier. Look at this. I said earlier, this is my evaporator. There's cooling in it. So from 4 to 1, and 4 to 1 is at my what? Low temperature. So it will be that. It will be the TL. For there to be cooling, temperature has to be very low, all over what? The work net. So it will be high temperature limit minus what? Low temperature limit. That is TH minus TL. That is for the evaporator. TL. So now, if you now move further, I will now go to the COP of heating cycle, heat pump cycle or heat pump. In the heat pump, it's always at the condenser where the temperature is very high, because the heat pump, the desired effect is for what? Heating purpose, right? It's for heating all over what? the work input, that is at the compressor. Now, as the heating happens at the condenser from 2 to 3, right? So I'm going to put Q 2 to 3 all over my work in, or I'm going to put the heat, Q is for heat, rejected all over, because at the condenser there's always heat rejected. That is why it moves back, it changes phase from gaseous as state 2 to liquid as state 3, changes phase. So all over what? The work in. Okay, if I like, my work in this case is equal to what? W1 to 2, because it is as what? The compressor. So this is what we have, any of these three. But in terms of temperature, the C.O.P of the heating cycle will give me the temperature that we expect in the condenser is what? If you look at it, this is 2 to 3 and this is 2 to 3, and that is what? High temperature. So the heat, for you to have heat, temperature have to be high. The higher you go in temperature, the hotter it becomes. So all over the high temperature limit minus the low temperature limit. So this is what we have. So you need to know this in your head. And also we need to understand that the COP of the heating cycle is equal to what? The COP of the refrigerating cycle plus what? Plus 1. This is another concept. So all these things are very important. So we'll take an example and see how we can apply this process. So example 1. Now let's analyze the example. And the example goes like this. It says the condenser and evaporator temperature of a machine operating in a CARNOT refrigeration cycle are 30 degrees centigrade and minus 20 degrees centigrade respectively. The machine is to provide 20 kilowatts of refrigeration capacity. Determine from figure 1 the coefficient of performance of the refrigerator, from figure 2 the power required to operate in the machine. The first thing you do when you see questions like this, you need to write out the data. So solution, you write out what? The data given. I said the condenser is always at the high temperature, right? If you look at our analysis here, the condenser is always between state 2 and state 3, and state 2 and state 3 is always at the high temperature, TH. So that means my TH is equal to what? 30 degree centigrade converted to Kelvin, it will be 273 plus 30, and that will give me 303, right? So we have 303 Kelvin. Why the evaporator is at the low temperature, TL is equal to what? Minus 20 degree centigrade. If you convert it to Kelvin, to be 273 minus 20, and that will give me what? 253 Kelvin. Now we've done that. Don't forget, high temperature is always for the condenser, low temperature is for what? The evaporator, just like I showed you here. This is the evaporator here between 4 and 1, and that is TL. So from here, what is called it says the machine is to provide 20 kilowatt of refrigeration capacity. So my refrigeration capacity RC, which is for my refrigeration capacity, will give me 20 kilowatts. right? And we are now told to calculate the coefficient of performance. Now we know very well that for what? Refrigerator. We know very well that the COP, let's move forward here. We know that the COP of a refrigerating cycle is equals to what? The low temperature, since temperature is given, over what? High temperature of a refrigerator will give me all over minus what? TL. And this will now give me, what is the TL? TL is 253. All over TH is what? 303 minus 253. Right? And this will now give me, what do we have? It gives us 5.06. COP doesn't have any units. Now the next thing we are told to calculate, now this is for number 1, Roman figure I. Roman figure II. We are told to calculate the power required to operate the machine. You know that the power required is called the work rate, and that is given as what? Our mass flow rate multiplied by what? Our work net or work transfer. So W12, or you say your work net. Now we know that our mass flow rate is equal to what? Refrigeration capacity over what? Refrigeration effect. That is the formula for it. Now the refrigeration capacity is given to be what? 20, and the refrigerating effect, where do you feel the effect? Where do you feel the cooling? The cooling is as what? It is at the evaporator. So that will now be what? This. So that will be just this refrigeration effect at the evaporator, and we don't know what it is. So I will just call this, therefore my mass flow rate is equal to what? 20 all over what? Refrigeration effect. I will term it equation 1. Now, but we know very well that the COP, recall, the COP of the refrigerating cycle is equal to what? The refrigerating effect all over what? The net work done. Right? The net work done. So we're moving up because of the net work done. Now the COP of the refrigerating cycle is what? 5.06. The refrigerating effect we don't know, but the net work done here is giving us this W12. So if I make W12 the subject of the formula, if I make the W12 the subject of formula, I'll be having something like this. Now watch. Therefore, and put it here. Therefore, my W12 is equals to what? Take this one out and bring this one in. Refrigerating effect all over what? The 5.06. Sorry, 5.06. So this is what we have here. So you put, I'll call this to be my equation what? Equation 2. So substituting equation 1 and 2 in equation A above, right? So I should call this my equation A above, which is giving us work rate is equal to what? Mass flow rate multiplied by W12. So if I input my value here, my work rate now will now give me the mass flow rate given here is 20 all over refrigerating effect. So 20 all over refrigerating effect, 20 divided by what? Refrigerating effect, multiplied by the work net W12 to be what? Refrigerating effect all over what? 5.06. Now this will equate this. So my work rate will now be equal to what? 20 divided by what? 5.06. And 20 divided by 5.06 will give me what? That will give me 3.95 kilowatts. So that is my answer. So if you find this video helpful, don't forget to click on the subscribe button. Thanks for watching.